Okay, this is going to be an introduction to using the comparison test for series to determine whether a series converges or diverges. So we'll just outline what the test says and then try a couple examples to make sure it makes some sense. So the comparison test says, suppose you have two series, and these are both series with positive terms. So one series we'll call A sub n, and one we'll call B sub n. And basically what's going to happen is you're going to be given your series A sub n, and you're trying to determine whether that series converges or diverges. And what we'll be doing is, as the name implies, we'll compare it to a series B sub n that we know about. So let's read through the wording of the test. It says, if the series B sub n is convergent and the terms of A sub n are all less than or equal to the terms of B sub n for all n, then the original series we were looking at is also convergent. So there are two conditions we're going to be looking for. And then the other part of the test will say then if the series you know about, B sub n, is divergent and the terms of the series you're interested in are all bigger than or equal to the terms of B sub n for all n, then the series you're interested in will also be divergent. So as we do a few examples, I think these words make a little bit more sense, but just to think about it for a second, if we know that, let's talk about this first condition, if we know that B sub n is convergent, and we're saying all the terms of the series we're investigating are less than that, it kind of makes sense that the sum of A sub n will also be convergent, because the terms are smaller. By the same token, if we know that B sub n is divergent, but the terms of A sub n that we're looking at are all bigger than that, it makes sense that A sub n would also diverge. So let's try a few examples now. Just one quick note about B sub n, right? We're going to be comparing to some series B sub n. We want to know about B sub n, right? So at this point in our discussion of series, I think there are really two types of series we know a lot about, right? And those two types would be geometric, or the other type that we're going to know about would be a p-series. So we know a lot about when a geometric series converges or diverges, and we know a lot about when a p-series converges or diverges from things we've already done. So let's just refresh briefly on when a geometric series converges versus diverges. Same thing for p-series, and then we'll try a couple out. So make sure you stick with me through the examples. I know this part's a little wordy, but just a refresher on geometric series. Basically, geometric series converge if the r value is less than 1. The absolute value of the r value is less than 1. And they're going to diverge if the r value is greater than or equal to 1. So that's for geometric. And what's kind of confusing is for p-series, it's kind of the opposite, right? So it's actually convergent for a p-series if p is greater than 1, and it's divergent if p is less than or equal to 1. So make sure that these two ideas are comfortable before we move on to some examples. So we have one example here that asks us to determine whether the series of 1 over 2 to the n plus 1 in the denominator converges or diverges. And we're just going to work our way through the comparison test to figure it out. So let's go ahead and start by defining the series we're being asked about as A sub n. Right, in the language of the comparison test, A sub n was the series we're trying to figure something out about. So in our case, just so it's clear, A sub n is the series we were given, which was 1 over 2 to the n plus 1. Okay, so that's just going to be what we're looking for. So now we need to make a comparison. So let's start thinking about the comparison. We can compare this to, and as I start making a comparison, basically the way I think about the comparison is I want to choose B sub n to basically strip off any extra constants from a sub n. So in this case, you might notice that if we were to remove the 1 in the denominator, this series is now starting to look like something you know about. And maybe if I take one more step, it'll become a little more apparent. So again, based off of a sub n, I'm just going to say, get rid of this plus 1 in the denominator for b sub n. And when I write it as 1 over 2 to the n, that really means I have the quantity 1/2, right, to the power of n. I can write it that way since 1 to any power is still just 1. And as soon as I write it that way, I start thinking about the fact that we said b sub n should be geometric or a p-series. So which one does it look like in this case? This looks like a geometric series. So that means we can note that the b sub n series we've just defined is a convergent geometric series. And I'm just going to write a little note to remind myself that here the r value is 1/2, which is less than 1, and that was what we needed for a convergent geometric series. Alright, so hopefully in terms of the comparison test, you see that we've got one thing on the table. Let me walk back to the wording of the comparison real quick with you, just to make sure this next step is clear. So far we've just determined that b sub n, our comparison series, is convergent. So we've done this part, right? So then it says, if b sub n is convergent and all the terms of a sub n are less than or equal to b sub n. That's what I need to show next. If I can show that, then we'll be able to conclude that the original series was convergent. So let's see where we are. We just said that b sub n converges. So now I need to start talking about the size comparison. So let's just start writing a few things here. We can observe that, and the wording of the comparison test said I want to show that the terms of a sub n are less, we said, than the terms of b sub n. So terms of a sub n are going to look like 1 divided by 2 to the n plus 1, right? These are going to be the terms of a sub n. The terms of b sub n are going to look like 1 over 2 to the n. And you might be saying, well, we said 1 over 2 to the n is the same as the quantity 1/2 to the n, which is fully true. But I want to be writing b sub n in such a way that I definitely feel convinced about the comparison of size here. So let's see what you guys think. If this piece here has a plus 1 in the denominator, and that's the only difference between these two terms, adding 1 in the denominator makes for a bigger denominator, which actually makes for a smaller overall fraction. So that's what allows me to say that the terms of a sub n, which we have here on the left, are in fact going to be less than or equal to the terms of b sub n for all n values. So we seem to have met the two conditions of the comparison test. So the last thing we need to do is draw our conclusion. So I'll just say, thus, the original series, which was 1 over 2 to the n plus 1, converges, and as we start using many more tests, as we get all these tests out on the table, it's helpful to name the test that you're using to draw this conclusion. So I'm going to say it converges by the comparison test. That way, if I'm looking back at my work and I'm wondering why I went through these different conditions, I know which test I was using to draw this conclusion. So that's pretty much a thorough write-up for determining whether that given series converged or diverged, and that's kind of the expectation to show for a comparison test problem. So just to walk through those steps again, we defined the given series as a sub n. We established a series we could compare it to that we knew something about. In this case, it was a convergent geometric series. We established then that the terms of a sub n are less than or equal to b sub n. And that allowed us to conclude by the comparison test that the given series also converged. So hopefully that example makes some sense. I think because this video is already pretty long, I'm going to cap it off here, but look for the next video for a few more examples.